All right, it gives me great pleasure now to introduce the first speaker of NetPL 2016. The first speaker is Changhoon. So Chang is currently the director of system architecture at Barefoot Networks, the latest and coolest networking startup at the moment in the Bay, for sure, where he is currently working on the P4 language consortium as a co-chair of the P4 design working group. Before getting involved with P4, Chang was very active and he was part of Microsoft the Azure division, where he led several engineering and research projects that deeply contributed to the Microsoft Azure architecture. Chang is generally interested in programmable network data planes, network monitoring and diagnostic, network verification, self-programming and configuring networks, and debugging and diagnosing large-scale distributed systems. Prior to that, he received his PhD from Princeton University. And what's very nice about Chang's work is a lot of these research contributions, including VL2, Seawall, IQ, Ananta, and Seattle, are actually adopted in large production networks. So it's not just academic impact, but very large industrial impact. So without further ado, it's my pleasure to leave the floor to Chang.
Thank you, Marco. Good morning, everyone. So I'm Chang. So today I wanted to talk about the network data plane. Originally, I was thinking of giving a talk about P4, but obviously 20 or 25 minutes is not enough for me to give full details of P4. So I felt that I should give more brief introduction about P4 and talk about the other benefits and the potential use cases of data plane programmability in general. So the title is a little too ambitious because I'm talking about data plane mostly. But I also wanted to set the right expectation here that the NetPL community or network and programming language intersection have been working on a lot of great control plane problems, but data plane is opening up as well. So I just wanted to let you all know that there's some great opportunities here. Okay. So what do I mean by data plane programming? Again, I presume here that some of you may already have experiences in P4. In that case, first few slides may be a little boring, but please bear with me because I think that there are people who have done mostly control plane programming, not real data plane programming here. Okay, so basically by data plane programming, I mean capability to dictate all these things for every single packet that a device handles. So you can define your own structure of all possible headers and metadata. Of course, you can define how to parse and deparse the packets. Deparsing is the opposite of parsing. You can also dictate the forwarding logic, more specifically a sequence of custom match actions where both match and actions are customizable. You can also define how to replicate, resubmit, or even recirculate the packets. Or you can also define the way you structure, maintain, and apply all the necessary information for match actions, but still in the forwarding logic. Basically, the tables and the contents, how you can structure your tables, how you can carve out your memory, fast lookup memory to host this kind of information or not. Of course, you should also be able to collect and export forwarding statistics because without the right information, you don't know whether your devices are doing right or bad. So basically everything, almost everything regarding the packet processing and every single packet. But I'd like to do more. Right? Today, a lot of data plane programming is actually confined onto the upper half, but we expect that we will also be able to do this rest. For example, we should be able to dictate the way packet schedulers work. We should be able to dictate the way some packets are actually generated within the data plane. And then finally, we should also be able to apply some even more complicated non-forwarding functions such as encryption, decryption, pattern matching, regular expression, evaluations, and so on, again, to the packet. So here, one important point here at the last part is that you probably cannot invent or realize encryption and decryption in P4, but given that those functions are built somehow in hardware or other languages, P4 should be able to allow P4 writers to use or consume those predefined functionalities. Right? So why are we doing this? I just wanted to summarize the benefits of data plane programming. Of course, first of all, you can introduce new standard features or custom features very quickly. Right? It's just a matter of writing your P4 program and changing your P4 program. But also, another interesting thing is that you don't always want to introduce new things. Sometimes what you really want is removing unnecessary existing things. Right? For example, in my data center network or enterprise network, say I don't use MPLS. I don't use, say, IP multicast. Why should I consume all the resources, hardware or software resources, consumed to realize these kind of unnecessary functions for my network? So I can just get rid of them, and then that gives you, more robustness and simplicity and less bugs and less things to maintain, right? Plus, if you can remove some things, you can also relieve the hardware resources that are previously wasted by those features. And hence, you can use that hardware, say your SRAM or TCAM, to do something more useful for you. For example, I need much bigger echo table, I need much bigger routing table. Yeah, you can do that if you reduce your MAC table. Right? Greater visibility. I'll have another dedicated slide about this, but a lot of new monitoring and diagnostics information will be made available when you can touch your data plane directly. Modularity, you can just use the P4 programs that are written by other P4 writers. I mean, in software world, modularity, composability are so obvious. Everybody is just using it without consciously realizing the benefits of this. In hardware, no way, right? So we're changing that paradigm here too. Portability, as I said, you write your program once and then keep reusing it over different architectures and generations just by recompiling it. And finally, you own your own network, right? It's all the way down to the hardware level. And that's why, this protocol-independent infrastructure is happening everywhere, not just in the networking, but entire infrastructure industry is going to the protocol independent or software defined way, right? So you might have heard these benefits maybe a few times, but there are a couple other subtle but still important benefits. So I just wanted to emphasize those two things here. So the first benefit is actually mainly for the silicon vendors. If you imagine that you're actually developing the either FPGA or ASIC for the networking systems. Now, your engineers, your hardware engineers and architects don't need to worry about particular protocols. And that actually gives them a lot of benefits because they can now focus on much more important things that can be better done at the hardware. For example, what's the right data structure and algorithm for exact matching, ternary matching, and range search? What's the right ALU design for packet processing operations rather than general purpose operations, right? What's the right the best design for stateful operations such as counters and meters, right? So those things are great because you don't need to quibble about some protocols, benefits, and particular designs, how you can interpret these sentences in IETF draft or RFCs, right? Moreover, you also don't need to worry about the unpredictability of protocol adoption. Right? So there have been a lot of great protocol discussions in IETF or IEEE. I don't mean to, sort of give bad impression about particular protocols, but for example, maybe you might have heard about something like Trill that has been very big discussions over the past few years. it started with great, designs and motivations, but somehow, for whatever reason, the industry didn't move that way. And hence, the adoption of Trill and the implementation cost and investment that are introduced to make Trill available on real commodity chips largely wasted. For example, another example, I actually am one of the inventors of NVGRE encapsulation protocol, one of the network virtualization protocol. For some reasons, the industry didn't move that way. The industry adopted VXLAN, UDP-based network virtualization encapsulation headers. NVGRE took 5-6 years for the hardware vendors to realize. Largely not useful, right? So now, if you're hardware engineers and architects, you don't need to worry about those kind of things that much because you're now focusing on a much more generic functionalities and how to do that better and faster. And then now you can actually keep reusing that nice microarchitecture, protocol-independent architecture over generations, right? And if you think about it, that's the way CPU industry has been working for the past decades. This second benefit is actually about, or for the entire industry. So I'm not sure whether you realized it, but in the industry, networking industry out there, there is a huge tussle right now between the, or over this common SDK. So the reason why this is happening is a little historical. So maybe 10, 15 years ago, people all cared about switch CLI. There is one vendor CLI, and then the other vendor CLI. People felt that, oh, this CLI is way better than the other, but for historical reasons, I couldn't move to the other CLI because all the tools and management applications are written based on one CLI and so on, right? That's a bygone era. Nobody cares about CLI that much, especially these days, because now large data center providers and enterprises actually own their control plane, switch local control plane. They have their own OS and applications running in the switches, so they stopped worrying about CLI. Instead, now they're worrying about the control plane to data plane API, also known as SDK. I don't know why they're using this term SDK sometimes. I don't think it's the right term. It's actually the interface between data plane and control plane. That has become a hot spot. And as you can imagine, there is one large incumbent vendor's API style, and the guys who want to own their own control plane don't like that, and they want to apply their own ideas over different types of chips and targets. So they want to dictate the API. But in my opinion, trying to achieve common, flexible, transparent, and robust API is just impossible. I've never heard of any such common API. And to ensure, if you really care about flexibility, transparency, and robustness, I think you should really forget about the common part here. Right? You should instead be able to automatically derive your own API, again, by compilation and language techniques, and then keep reusing it. So even if your underlying hardware infrastructure changes, you own your own data plane program and hence your API, so your control plane programs don't need to be changed. So that's another important benefit in my opinion. So P4 is one language getting very popular and actually widely used in some sectors of the industries already. And we're doing this through the language consortium called p4.org. Everything is under a patch license. And the original paper written about 2-3 years ago by the industry and research visionaries are called P4.14 because it was standardized in that year. And then we're actually producing or about to produce the new version of that language called P4.16. Okay. So I'm going to talk about P4.16 a little bit in a few slides. And we're actually supporting various devices such as physical and virtual switches, host networking stacks, NICs, and middle box. Basically, any packet processing devices built with various types of targets, programmable targets. And then we also want to enable a wealth of innovation, large number of different applications, new applications, and then very low barrier to entry. So Now, I assume that you know P4 a little bit here. Now, I just wanted to talk about P416 a little bit. So why do we do this and how do we do this? I just wanted to summarize that in 2 or 3 slides. So P414 was great, but one design flaw it had is that it actually assumed that P4 is going to be used only for switches. But people realize that P4 is usable for any packet processing devices, like firewalls or NICs or even end-host networking stacks, middle boxes. So the users of P4 wanted to apply these P4 techniques to various different types of architecture, packet processing architecture. And to achieve that, we introduced this notion of architecture language separation. So I'm going to talk about that in the next slide. And then we also introduced in P416 something called extern types. Basically, it's kind of black box objects of which interface is defined in P4, but the implementation is done otherwise, using hardware language or C or whatever. But your P4 programs can still import them and then use them without actually worrying about or polluting the language largely. Another important aspect of P416 is actually improving reusability of the code. So basically portability and composability. In P414, this aspect was weaker, so we put a lot of emphasis here. And then the way we do this is using standard architecture and standard library. So as long as you use the same standard architecture, even for different types of devices or target architectures, you can still ensure decent portability of your P4 programs. And a lot of other, standard techniques that you can use at, programming languages, we borrow them, like local namespaces, local variables, sub-procedures, and parameterization. These are all helpful for composability. So let me briefly talk about this architecture language separation concept. So the architecture is something that the target provider offers for their, target consumers. So it's like these generic descriptions of the programmable blocks in that particular target. So here I'm saying that, hey, on my target, I have one parser. It can consume the byte stream of packets, and then it generates a parsed representation of the packet called headers. And then that type of the headers is actually defined as a parameter. It's generic type. So the user of this parser can define their own header sets. And then I also have ingress match action pipeline, which also takes these headers, the same type or parsed representation, along with some intrinsic metadata that the hardware offers, plus the intrinsic metadata that hardware can understand. So intrinsic metadata is like, control registers in the CPU world. And then I also have one deparser here. And then by combining these 3 programmable modules, parser, ingress, pipeline, and deparser, I define my own switch. Okay, so that's the rough high-level description of my switch architecture. And then the user of this architecture or device, when he or she writes the P4 program, she will do this. It includes the architecture.p4 for this architecture, and then it defines its own, or the implementation of its own parser, ingress pipeline, deparser goes here. I just omitted them. And then she can now finally instantiate a switch of this type by using this. Okay. So that way, the language remains stable and can be useful for many different architectures. Some architectures may have multiple parsers and multiple match action pipelines. Doesn't matter, you can still describe that architecture. So fitting all this together, the P4 language consortium is working to define the standard architecture and standard library. And then each target provider will or can come up with its own target-specific architecture, which could be usually a superset of this standard architecture, and again, a superset of this library, including their own standard or target-specific library. When you write your own P4 program, the first thing you have to do is choosing the right architecture. Am I going to use just the standard architecture or a little more target-specific architecture? And then you write your own P4 program, and then in that P4 program, you can import standard library objects or target-specific library objects, or even your own user library objects, and then compile this along with the architecture and the P4 program, and then this compiler will generate two outputs. The first one obviously is target data plane configuration. So if you have, programmable networking ASIC, it will be, configuration or the values of millions or tens of millions of registers. If it's FPGA, it's a different output. And then it also auto-generates the API, as I said, because if you have your own new tables, you need your own new access functions to be able to add, delete, or modify the entries in the tables. Right? So that's the development model. P416 also has a few more interesting points, such as sequential execution semantics. So in P414, each custom action was meant to be interpreted as parallel or parallelizable primitive actions. It's hardware friendly, but not human friendly, definitely human unfriendly. And then we felt that could be a hurdle, so we felt that the interpretation of that section should be now sequential, but that doesn't preclude parallelization opportunity. We're just pushing more responsibility to the compiler. Compiler should be able to parallelize these things on behalf of the human writers. Okay. We're now supporting expressions, so the P4 language looks more like other types of languages, common languages. We also embraced, of course, strong types. Explicit deparsing is also possible. In P414, your deparsing logic is just inferred by the compiler from your parsing logic, and we figured out that sometimes this can introduce ambiguity or restrict your capability. So in P416, you can explicitly define your own deparsing logic. And more importantly here, starting with P416, we'll say that all the subsequent minor versions of P416 will have to be backwards compatible with P416. Okay, so P416 is really the standard or very reliable safe ground. And this may, actually, you might have realized that P416 is not exactly backwards compatible with P414, but don't worry about it. We have already, 14 to 16 translator. So if you have already started writing P414 programs, that's okay. You can translate them automatically using this tool. So now, what's next for P4? We need packet generator sub-language. A lot of programmable devices started to actually have this embedded packet generation logic in the data plane. What's the right sub-language to be able to describe that logic? And the reason why this packet generation is actually very interesting and powerful is because if you combine packet generation and stateful processing, you can actually do event-driven programming in the data plane. Standard architecture, we currently have just the architecture description at the P4 level and a reference implementation of that architecture in software in C, and then expect that other standard compliant architectures will behave similarly. But that's a very vague term. And some people think that, hey, we should actually introduce formal specification to be able to describe the standard architecture's behavior more rigorously. Scheduler sub-language. You might have heard about a few research outcomes. For example, the Pi4 work, which will be presented tomorrow here at SIGCOMM. It's an attempt to introduce reprogrammable packet scheduler. So some hardware support like that may appear in a few years, at least for lower speed devices. Then the language should also be able to allow users to program those kind of schedulers. What's the right abstraction for that? That's a good research topic. So we need your contributions and suggestions here. Now, so before wrapping up, let me just briefly talk about a few interesting and new opportunities that are opening up here. So network monitoring, analysis, and diagnostics is definitely going to be very, very exciting with programmable data plane. And here is a few reasons. So monitoring features have always been second-class citizens in these high-speed networking chips or devices. And the reason is because whenever you need to devise the next generation of very fast networking chip, or ASIC, for example, the hardware engineers are paranoid about achieving that speed. Plus the very basic features like, routing table lookup, MPLS, multicast, or whatever, the very basic features. And then going to the next generation speed with new architecture, with all the feature set is extremely, extremely challenging. And therefore, they always have to make a cut decision and trade-off decision at the feature level. And then monitoring features never win. Because if you, imagine this, if you have, say, 6.4 terabps chip, but sometimes, routing table lookup doesn't work well, or you don't meet actually 6.4 terabps, it's actually working at 5 point something, then that chip has no chance in the market, right? But if you have a chip that works actually at 6.4 terabps, does all the basic things, but very poor on monitoring, it still has some chance in the market. So they always cut monitoring features and diagnostics features. Right? With programmable chips, they don't even need to, and they cannot make such trade-off decisions for you because they're not building protocols in hardware. Hardware is doing something else, much more generic primitives, right? So that's really good thing because you, for example, if you can get rid of MPLS or VLAN or IP multicast that you don't need, you can use the hardware resources freed up by removing these features, and then you can realize your own monitoring functions. Another thing, network monitoring or better monitoring for infrastructure in general is not something that can be achievable using a Zen-like approach or an epiphany. It's not like that. Better monitoring always comes realized through better iteration and longer mileage. Everybody starts, even when you write your own applications, CPU applications, you start with sort of crappy monitoring logic, but it gets improved because you own the feature, you own the program, you use it, and then realize that when you see a bug, oh, I didn't have the right monitoring logic, so I have to go change this program to monitor these other events, better logging information. Over time, it gets better, and then you have great monitoring and visibility. In networking, we never had that opportunity of improving or accumulating this improvement because the network owners could not program their network devices. But interestingly, of course, the network owners and admins know what to monitor best and how. So by this alignment, through this alignment, we can get better, monitoring, analysis, diagnosis much better easily. And as a matter of fact, a lot of powerful new approaches are actually emerging in this domain. So in-band network telemetry, basically capability to use every packet as a log packet by embedding the metadata information to the packets is something that is happening right now, and then I'll actually give a demo this week later. Advanced mirroring and reachability monitoring directly within the data plane, all those things are happening now. To push more into and out of the data plane at the same time, it sounds a little crazy, but both actually can make sense in different contexts. For example, people want to put more into the data plane, like middle box functions, layer 4 load balancing functions, some security functions such as whitelisting, DDoS detection, mitigation, SYN authentication. Some of those middle box functionalities that need to be done at full line rate, such as throttling, can be done in the switches. That's very powerful because now you have 6.4 terabps, say, layer 4 load balancing capability. That's 2 orders of magnitude improvement over the existing appliances, right? Some people even wanted to offload some application logic into the network data plane. For example, NetPaxos work published at CCR. You run part of Paxos consensus protocols in the network data plane, and hence the throughput of this Paxos and latency is improved again by 2 orders of magnitude. Now, application is lagging behind. Mostly ordered multicast published at NSDI last year, and switch KB work published at NSDI this year. These are all interesting and exciting examples of taking advantage of the new capabilities in the data plane. In the meantime, you can also think of getting more out of the data plane. So for example, imagine that you have per packet metadata attached to every packet. Every packet is carrying its own switch ID, sequence of switch IDs that it has gone through, hop latencies and congestion information. You can actually expose this to the transport layer, TCP or UDP, or you can even expose this through a separate channel through your extended socket to your applications. So imagine that your application can actually see per packet path and latency or link utilization. There are some crazy application programmers who would love to get this kind of information and take advantage of this opportunity. So this is the final slide. So if you go this way, how far can we go and what can we do? So for example, in maybe, at least in my mind, in 5 years, 10 years from now, we'll have largely, made this entire network programmable because both control plane and data plane are programmable, right? Now, then, can we auto-generate even P4 programs, right? Then, what's the input for this P4 program generator? It should be something like networking policy description, but what are the right abstractions for that? What kind of new languages do we need? When do you want to regenerate P4 programs? Only at the compile time or even at the runtime? Right? How much can we additionally verify when all aspects of networking are programmable? Compile time verification, there has been lots of research work here in the community, especially from the control plane point of view. But imagine that you can actually see what the data plane does and then dictates that. You can verify even more, again at the compile time and the runtime. Stateful data plane algorithms are useful and feasible, but how far can we go, right? So, for example, Conga work published at last year's CCOM, it's a good example of stateful application because control plane gives you multiple choices. These are all valid paths, but data plane choose the real path for individual packets or flowlets. So control plane doesn't actually get involved in the actual details. How much can we do further there? And then what's the right development abstractions and tools for them? And finally, can we build a network without any switch local control plane? Why do we need switch OS at individual switches? And obviously, for example, Ethernet doesn't work that way. Right? Ethernet can work just by learning. And if you think about source routing and INT-like capability, you can imagine that, I don't really need any control plane logic at individual switches. I just need logically centralized controller. And the data plane I completely dictates. I micromanage every single packet. Then why do I need something like, switch local control plane? And is it actually helpful or bad? Another interesting idea. Okay, so with all that said, I'll conclude my talk and then I'll be happy to take questions.
Thank you, Chang. So we have time for question. I like yeah, go ahead.
The idea of before is it increasing the requirements over the hardware of the network? Are you increasing the requirements on the hardware, on the network hardware, when you are using before?
Yeah.
Because you have to process a little bit more data on the hardware, on the data plane hardware. Don't you?
So are you asking whether we're actually asking the network owners to do more than what they can do? Or more than what they have been doing?
I would like to see a comparison between the hardware requirements with before and without another SDN approach, like OpenCode, for instance.
So the hardware has to be fully programmable to be able to enjoy P4. Right? If you have fixed function hardware, even if it implements, say, OpenFlow 1 dot something, you can do only so much. For example, with OpenFlow, you cannot define new headers. You cannot define your own custom actions. You cannot change the orders of table executions like that. So the hardware has to be more capable, yes. There is that. Yep.
So I have one question, Chang. So first, thank you very much for this very nice talk. So what do you think that, the majority of the audience here, are academics, right? And there's a lot of industry weight being thrown at the moment behind P4. What do you think that are most effective ways for this community to be able to both at the same time help out, but also not be in a straight competition to industry? Like I wouldn't want to do a project on something that the month after Barefoot comes out with a better version already. So which ways would you encourage people to pursue to be most effective in contributing to the development of this type of programmable data planes?
Writing P4 programs is something that everybody can do, and then I don't think target providers will be able to do that better than the actual users, as I said. Especially research and academic communities can come up with very interesting ideas, and also, say, large online service providers and enterprises, they do have very interesting requirements. For example, we talk with a few different industry sectors, for example, financials and medicals. Whenever I talk to them, I'm amazed at what kind of strange requirements they have. We don't know. As a target provider, we don't know. As P4 Language Consortium members, I also don't know. P4 is just a tool, but better applications can always come from the application owners, or especially the network owners, or the distributed app owners, or compute app owners, or storage app owners. Yep.
Oh, yeah, go ahead.
Do you think that P4 programs in the future will be open source? I mean, for instance, I buy a router from Cisco and I get a P4 program with that. And then if it's closed source, I am at the same point where I am now at. But if it's an open source program, I can modify. Is there any...
Yeah, all the things contributed at P4 Language Consortium, the GitHub, are all open sourced under Apache. So that includes front-end compiler, P4 compiler, and the behavioral model switch, basically software P4 switch, and the back-end compiler for that. All the reference P4 programs that realize existing protocols, plus some new interesting protocols like INT, those are all open sourced under Apache.
Yeah, my question refers to the hardware vendors. How do you confirm? How do you negotiate this with hardware vendors? How do they push them towards open sourcing their P4 programs? So it's just...
Yeah, I think the P4 programs will still remain as open sources. Are you worried about the hardware design and the chip itself being closed?
I'm worried about the hardware vendors who actually sell hardware and also sell the P4 program with that. And they actually just, if it's closed source, then the whole hardware...
I see.
How do you convince them to not, go in this direction? Let me somehow modify.
So then that requirement has to come from the users. You say that, hey, instead of having, I don't want your devices running this kind of features. You have to ask that, hey, I want programmable devices. Give me your P4 programs in addition to your device and black box system, right? Give me the compiler and the P4 programs that you used on this device to realize these features so that I can further modify, right? Yep.
Yeah, there's a question.
During the talk, you have mentioned some of the things that the API generation and the parallel execution of the primitive can be pushed on the compiler, the compiler. So, but in the specs and all, are you planning to have a specific part, or do you guys have any recommendation for the compiler designers how to provide with the language? Because we have seen there are a lot of things going for the FPGA and the names, everyone is working on their sides of compiler. But there is no specific guidelines, like they're using different IR and then compiling for their targets. So it's not helping to the people also, because the spec says, okay, we need to achieve these things, but when you go through different target methods, it's being difficult to
Yeah, that's right. So the front-end compilers, that's why we actually open sourced it at the P4 Language Consortium. And front-end compiler has to be common across all the P4 programmable targets. And the precise purpose of doing that is actually standardizing the IR. But the back-end compiler, I don't think we can standardize it, because every target has different characteristics, right? Different opportunities for optimizations.
Any idea about this kind of feature you need to support to say that we are supporting
Yeah. Yeah.
Do you have any subsets saying, okay, this has to be supported?
Yeah, yeah. I mean, there is no exception. Any programs that are written with the standard P416 must be compilable on any P4 programmable target. If not, that is not a P4 compliant target, right? But performance portability or resource portability is a different issue.